let's just keep rolling along. So this is section 11.5. We're going to look at derivatives of logarithms first, and then derivatives of exponential functions following. And this is really an application of the chain rule that we just went over in 11.4. Change out my computer glasses. It's a little clearer, a little more focus. Okay, so for this one, get over to here. And let's go with blue. When we take the derivative of the natural log of x, it's simply going to be 1 over x. And where the chain rule comes in is, as you notice, if the input to the logarithm is something more complicated than x squared, or something else, we think of it as u as some sort of expression. So we take the derivative, it's going to be 1 over that expression times the derivative of the expression. We'll work a few examples like that. Now, if it's a logarithm with a particular base, so this is natural log is a log base e, and it just so happens, notice that when you have any other base, you get 1 over x, but you get what I call a sort of a correcting factor, because this is natural log of the base, which is just going to be a number. So it's sort of the same principle, but you've got, just think of it as again, a correcting factor when it's not the natural log, the log base e. And that's just because with exponentials, e is this number 2.718 ... that just naturally has this power. It's kind of cool. It's its own derivative. It really is sort of just naturally occurring. It's a very important number for our system. Okay, so we'll work a few examples here and we'll just see how it works. So again, it's just there's no subtracting of exponents or anything like we've done before. It's simply when you have the natural log or any log, the derivative, whatever's inside the log, it's 1 over that. That's its derivative. And I've seen ways of trying to explain it and go through it, and it's at some point you need to kind of just take a leap of faith and say that's what it is, because it works. Okay, so this first one, we just need to take its derivative. So I'm going to give a little bit more room here. The derivative of y prime. Okay, so thinking of chain rule thing, here's a constant, so that's just a constant multiplier. Those just tag along. Now the derivative of natural log of 2x, so what is inside the logarithm? 2x, so the derivative is going to be 1 over 2x. And then the chain rule says now we take the derivative of the inside stuff. It doesn't go down in the denominator, just what is the derivative of 2x, right? That's the inside, it's just 2. So we multiply by 2. So that's how it works. Constant multiplier tags along. Derivative of a natural log is 1 over whatever stuff's in it. And then we multiply by the derivative of that inside stuff. And then we simplify. 9 times 2 is 18 over 2x. And then 2 can divide into 18, so that's going to be 9 over x is our final answer. Okay. Got about 4 of these to do, so and I think they're all natural logs. So so when we take the derivative of this one, again, natural log of stuff is 1 over stuff. That's what it is. Now, using the chain rule, we multiply by the derivative of the stuff. So taking the derivative of the inside, we get 3 times 5 is 15. Subtract 1 from the exponent, that's x to the second power. for the second term, 2 comes down in front. 2 times 1 is 2. Subtract 1 from the exponent, so 2 minus 1 is 1s, which we don't write. You could put it there, you don't have to. The derivative of 4 is 0. So you could put a plus 0, but we don't need it. This is our answer. And so I'm just going to, we got lots of space over here. I'm going to say that derivative, I'm going to put that in the numerator. 15x squared plus 2x all over 5x to the third plus x squared plus 4. And now if they factored something you could simplify more, that's more of an algebra thing. The calculus, we are done. We're done with the calculus. So that's this one here. I guess I should circle my answers, right? Or box them in, right? Okay, natural log of this absolute value. Now we didn't look at the specific, but when you have an absolute value, the absolute value remains there. Okay, so again, the derivative here is going to be 1 over x to the third minus 8x absolute value times the derivative of the inside. So the derivative of the inside is the 3 comes down, we get 3x squared, 3 minus 1, the box down 1. And this one, 1 times negative 8 is negative 8. Subtract 1 from the exponent, we get x to the 0. So that's what we're left with. And put our absolute values there. I'll be honest, I kind of breezed over the absolute value ones because I looked real quick and it looked like all you really needed to do is keep the absolute value. So I'm going to take a quick peek here. They take the absolute values off. What I saw in the text was having the absolute values. We'll come back to that, but that's basically what we're going to look at. And then let's look at the last one. Again, we see we got 9x, 9 over x for the first one, so that was correct. Let's give ourselves a little bit more room. And this one, we're now going to need to use the product rule as well. So that gets us back for what we did actually before spring break. So the derivative of x, that's term by term, that's just 1. Now when we take this derivative, it's going to be minus, I'm going to put a big part, what is x times natural log of x? Remember when we did the product rule, when you have two things multiplied, say a times b, I guess let me make sure that this is here, you get the derivative of a times b with nothing done to it plus the derivative of b with a having nothing done to it. Okay, and in this case, first one's a, this could be b. Okay, so we take the derivative of a, which is x, derivative of x is 1 times natural log of x. Then we take the derivative of b, natural log, its derivative is 1 over x times a, which is just x. Okay, so what we end up with is 1 times natural log is just natural log of x. This we get x over x, which is 1. Okay, so that's our derivative. That's what goes in here. Natural log of x plus 1. But notice, where are we? This negative here is going to distribute through. So then we get y prime equals 1 minus natural log of x. This distributes there, minus 1. 1 minus 1 is 0. So we get y prime equals negative natural log of x. And again, we can check our answers. It did simplify pretty good. They did show all the steps, which is good. but that's what we end up with. So we'll box that one in too. Excellent. So let's move on to exponentials. And the exponential rule is the exponential, the natural number, its derivative is itself, e to the x. Any other exponential, any other base other than it's itself times, again, this correcting factor of natural log of the base. Very similar to what happened with logarithms. Okay, and again, this is really the reason we do this after the chain rule. Is the main thing is there's this the exponent itself, say like down here, can be more complicated than just x. So we get e to the expression times the derivative of that expression. Okay, so for here to take its derivative, let's just go over here, the derivative of y. Okay, so we're multiplying by 4. That's a constant multiplier. It just tags along for the ride. The derivative of e to stuff is e to stuff. That is its derivative. It's kind of weird. It's its own derivative. That is the derivative. What we're left to do now, though, is to take the derivative of the stuff, the inside stuff. Okay, so x to the 5th, its derivative, the 5 comes down, subtract 1 from the exponent, and we have x to the 4th. Negative 3x, its derivative is going to be negative 3. And then x to the 0 power, so that's why that's 1. This is our answer. Now we can distribute through, and I guess why not? We could have our final answer, y prime, take the 4, distribute it through here. We get 20 x to the 4th minus 12. Now the thing is, we really need to have all of this, it's all of this times e to the x. Yeah, be careful how I just don't want people, so that's the exponent, and I'm a little touchy because sometimes I forget to bring it down when you're entering it in the calculator. This is 3x up here. Okay, and actually this would distribute to both of them, but we can leave it like this, or you can distribute it through. I'm not quite sure what they do, but this is a good answer here. Again, the rest is algebraic simplification. Okay, so this one, we're going to deal with not only the chain rule, but also the product rule. So just like we reviewed the last one, let's get a little bit more space up here. When we go to take this derivative, think of this part as A, this part as B. Okay, so this here. So we want the derivative of A, and remember, by product rule, when you take the derivative, you get derivative of A times B plus the derivative of B times A. Derivative of A is going to be 2x minus 2. So I did that, is the derivative goes there, times the B part with nothing done to it. Of course, it's going to be hard to tell the difference, right? And then we're going to add the derivative of B, and again, the derivative of B is just e to the 2x plus 3. It's itself, but then we have to use the chain rule up here, the derivative of 2x plus 3. So the derivative of 2x is 2, derivative of 3 is 0, so we get that part, and then we need to multiply by A. So that's our answer. How do we want to simplify? Again, we could distribute through here. And then notice that there's an e to the 2x, so we could factor that out. Again, just using algebra factoring. I'm not sure. I haven't really, I don't remember what the answer was. I probably have looked at it, I'm sure. So I'm taking the e to the 2x, I'm factoring it out. And then what we're left with is 2x minus 2 plus, let's distribute this 2 through, 2x squared minus 4x. Okay, and by doing this we can, we do get a little 2x minus 4. There are some like terms in there. So we get e to the 2x plus 3. I'm going to bring the 2x to the front, 2x squared. 2x minus 4x leaves us a negative 2x, and then a minus 2. Now, if you wanted, you could factor out the 2, but I think we'll leave it like that and call that good. This G question, again, it's just take the derivative of the outside, then take the derivative of the stuff. So what I'm going to do is rewrite this as e to the 5x to the minus 1, because it'll make taking that derivative a little bit easier. You could leave it this way, but just remember that that exponent is 5x to the minus 1. So just because I think the answer will probably leave it as 5 over x, we're now going to multiply by the derivative. The derivative of 5x to the minus 1, the negative 1 comes down times 5, so that gives us a negative 5. And then you subtract 1 from the exponent, negative 1 minus 1, we get x to the minus 2. Okay, so the way we could write this, we could put this x to the minus 2 in the bottom, in the denominator, and rewrite this as minus 5e to the 5 over x, all divided by x squared. So when you move it to the denominator, it becomes positive. Okay, just to make it look a little prettier. And let's see, I think that's the last of them. So the first answer, we see, did they factor? They did. Actually, they even factored a 4 out of all of that. Yeah, you could factor a 4 out, or leave this 4. You get the 4 out of there. Oh, they just left the 4 on the outside, and that's all they did. Okay, so they left it out here instead of putting it in there. Okay, for F, yeah, they went ahead and factored out the e to the x. I got off on mine, so they got the same answer we've got over here. They just put it in front instead of the back. In multiplication, you could put it in either order. And then we've got this one, which they went ahead and left with the negative exponent. That's fine. Don't fault them for that. This one, I think, just looks a little prettier. But then you've got a fractional exponent and this. So again, algebraic difference of writing it. Okay, so both are correct. So that brings us to the end of 11.5. We'll take a look at 11.6 next. Thank you.